Thank you for your interest. It's wonderful to see this room full of people. I'm Valentijn, Vice President located in Europe for ARC Advisory Group. I lead this session. I took that over from Mike Guilfoyle, who you maybe saw this morning. And we'll speak about machine learning in the real world. So we'll have some real world applications. Do I have a clicker actually? Looks like I don't. Next one. Sorry for that. Very briefly, we'll do some presentations just after this. I would like to introduce you briefly what machine learning is, what I found that machine learning is, and how it differentiates from other techniques. Just to create some clarity, to get some confusion out of the way. I'll give a few suggestions on other possible real-world applications and benefits. We'll present then the presenters, and then when we are done with the presentations, I'll also present the panelists. That's okay with you. Next. So we have Adam Juchter. So I'm going in alphabetical order. Adam Juchter from Azure IoT Suite, executive from Microsoft. We have Harry Menon from Symphony Industrial AI, who will present a case about, that will be easier. Thank you so much. About a mining application. We have Sastri Meladi sitting here from Foghorn Systems, and we have Iyad. There are several spelling for your names running around. Buhalaiga, is that okay? Okay. From Saudi Aramco, we'll speak about machine learning to recognize flares from images. So to make this a little bit more modern than hands up. So my question is, who are you? So you need to go to your app, your forum app, and go to polls. And then in polls, you will find our session. Please go to your app, your polls. And then please answer this question. Okay, there we go. Okay, seems to stabilize. So we have about a third machine learning users. We have about a third the machine learning vendors and service providers, and we have about a third of other users. So excellent, wonderful. We'll have a few more questions for you later on. Good, so let's have a look at what machine learning is. The term was coined in 1959, so it's not really that new. And there is a good operational definition from 1997 that says it's a computer program that learns from experience with respect to doing tasks and increasing its performance in doing those tasks from that experience. Right? So it is doing stuff based on experience. It will improve doing those tasks. It is working without explicit instructions, and it relies on a model. So we'll speak about the model in a second, and inference. So you need to develop a model from training data, and we consider it a subset of artificial intelligence. So that's the basis. Now, there are other fields that use similar techniques, such as data mining. So there are many, many overlaps, but it doesn't have the same objective. And one is particularly interesting, I think, is optimization. Real-time optimization in the petrochemical and refining industry has been here since decades. And so the question is how far is that different, and how far is it similar? So optimization minimizes the cost or loss function on a given training set, right? So we know the data, we train it, and we optimize the fit, so to speak. In the case of machine learning, we minimize the loss on unseen samples. And that's why it can improve, because it hasn't seen everything. Does it make sense? Check. Okay. There are several types of machine learning algorithms. There are the supervised learning algorithms that know both the inputs and the outputs, the causes and the effects, and trains the model on both. You have the unsupervised learning, where you have only the inputs and you try to model the outputs. And then there is semi-supervised learning, where you miss some of the outputs. And then finally, there is reinforcement training, where we can really help the algorithm to learn by saying this was the right decision, that was the wrong decision. So that's in terms of learning. And that's not exactly the same as processes and techniques. So we have, for example, feature learning that modifies the representation of the input data. Many of you have probably seen principal components analysis. Now, it models the data around in a way, presents it in a way that it starts making sense for you. We have anomaly detection or outlier detection. It's obvious that we can use that to detect when an asset starts getting problems. So a very popular application in industry. There is decision trees. These can be classification trees according to discrete outcomes, or they can be what they call regression trees with continuous outcomes. And I'll give an example of that. And that there is association rules that works a little bit like the brain that associates different things. So the decision trees, this is an example I found by coincidence in Belgium by someone who's doing energy analytics. This is behavior that you see in all process industries. It is the energy intensity compared to the capacity. So the higher the throughput, the more efficient we become by amount of material produced. That is intuitive, right? However, you see that depending on maybe the grade or maybe the process conditions, those curves are in parallel, and some are more energy efficient than others. So now analytics could help us figuring out which process conditions, which grades are more energy efficient. And this example that I don't know the details of, but you see how this tree works. Basically, this is all the data. And part of those data, when the steam extraction in liters per hour is smaller than some number, we have actually quite energy efficient operation. And in the other cases, we have all the other cases. And then we can find another split in conditions that define the other operating points. And you see the result here. So you can, there are ways that you can find out the process conditions that help you finding the more energy efficient operation. So that's an example of application of a decision tree. Anomaly detection, of course, used in asset analytics. I took a few diagrams here from the company Bazan in Israel. And as a background, maybe you know or maybe you don't know, but valves in the process industries are usually a source of problems. They start sticking. They move in chunks and not gradually. They create all kinds of problems. Sometimes they don't close exactly if you want to, and so the indications are that the process value doesn't move when apparently the control system should have moved the valve. So you lose the correlation between the process and the variables. So here you have an example. When we move the steam valve, you get some temperature change. And here you move the steam valve and you get some temperature change. So that's normal. Where it is not normal is when you don't move the valve and you do get temperature changes. So this particular case, Bazan found was actually the steam valve was leaking. It didn't close. So you got temperature changes without really wanting it, without really sending the order to do that. Another issue was with flaring, and that ties back a little bit to the presentation by Saudi Aramco later on. This company is very close to the city of Haifa, and when they have valve issues, sometimes they have to flare. That's an environmental issue. The whole city can see it. The television is looking. So it's very uncomfortable for them, and so they try to avoid that, like everyone else. And in hindsight, you can see that before the flare actually happened, there were issues with that valve already, were even visible to the human eye. Of course, there are also issues that are not visible to the human eye and that you can figure out with anomaly detection. The company providing the analytics has in the meantime been acquired by Samsung, and there are some representatives sitting here. So if you want to know more. What we will see also in our presentations is models that we use to train the data. And so artificial neural networks is important to know about. They sort of loosely model the connectivity of the neurons in the brain. And they are, let's say, mathematical nonlinear functions that transform an input to an output. And of course, there is an adjustment of the coefficients to get the output. And those models are extremely flexible, and you can model many shapes. And it is even so flexible that for process control, it introduces some risk. Because when you extrapolate outside of the training area, you could get behavior which is not non-physical. So it has advantages and it has risks. I'll not go in detail into optimization because Harry is introducing that in a very instructive way. But what usually happens is that the plant is operated in a region which is experienced or perceived to be safe, where the optimum is usually lying somewhere further away in an area where we don't have many operating points and experience. And usually it's at the border of behavior that could become a problem. So there is some risk for operators that don't like to operate there, and optimization can help us getting there in a safe and consistent way. Finally, I'd like to make the link with traditional control technology, which is advanced process control. Advanced process control has an empirical dynamic process model inside. And that model is approximate. And so in each point in time, we have control variables that we want to move to some value, the CV1 and the CV2, the red and the blue. And we have manipulated variables that we can change in order to get those control variables where we want. And that model will predict that for us. However, we know the model is not very accurate. So what we need to do is we need to calibrate that model. And so we make predictions of where the plant will go in a certain number of time slices. And each time slice, we will do that optimization, make that prediction, and calibrate the model. So we are learning from the experience from the process. So in a way, this is also machine learning. It may be, let's say, more cumbersome to put to work. It is more traditional, but it's also machine learning in a way. And in Harry's presentation, you will see that both traditional and more modern approaches will meet each other, which I find very, very interesting. So potential applications in the real world, others than the ones we will see, is predictive maintenance of rotating equipment, valve actuation issues, abnormal process conditions, optimizing steady state conditions. And of course, you can use that to integrate that in more complex processes, such as reliability or energy management or quality management. And so there are many, many applications that we still haven't touched upon with those new technologies. And there is a real fascinating era ahead of us, I believe. Okay, another poll. where do you stand with real-world machine learning? That's a fantastic tool. Planning and implementation, about 30%. Implementing, 15, 16. Managing a global machine learning implementation, 20%. And other, 40%. So those are probably people investigating or thinking about it, or changes a little bit. Excellent, thank you very much. Will be also useful to use these data in our publications that we make out of these sessions. Challenges related to machine learning. It's too bad we can't see the questions here on screen. No votes? Opportunities related to machine learning. Can you center on the screen? Okay, it seems that we have a little technical challenge. We would be excited to see the numbers now. There is an issue in the app? Ah. I see. Okay, guys, forget it. Never mind. In any case, thank you for your votes for the two first questions. That's wonderful. Okay, let's move on. And let me introduce Harry Menon. He is CEO of Symphony Industrial AI. His company focuses on operational excellence solutions for the asset-intensive industries. In his past, he's been working on operations management and supply chain management in many well-known high-tech companies. He has well-known engineering and business education. And the floor is yours, Harry.
Thank you.